As I kind of alluded to in the last podcast, the deeper ocean does something really cute. Near surface, we had related the pressure gradients to free surface elevation gradients in the x and y, which again, to repeat, if the altimeter is sitting at 1400 kilometers above the surface, using the laser can give us sea level map, then we can easily take gradients of the sea level and derive surface currents, right? But what happens, so that's the surface geostrophic currents. We had already seen this. What happens below the surface? The atmospheric equivalent of that, of course, is U geostrophic is G over F Z hat P cross grad P Z, where we finally got rid of rho and used the pressure coordinates and derived a expression that is normal to the unit vector that's normal to the pressure surface with height contours on pressure surfaces. So we had said before that height contours on pressure surfaces in the atmosphere are streamlines of geostrophic flow. That's what this is basically saying. In the ocean, the difference in sea level between 2 points over which we are looking for geostrophic balance can be estimated this way: F times L, the horizontal scale of delta eta, times U, the typical magnitude of the geostrophic current, divided by G. And it turns out that if you look at maps of sea level, this is something that is in fact measured by a satellite altimeter, average over 10 meters, 10 years. You see the typical characters we expect. The subtropical gyres, we will see later on, are converging, which means water is being pushed down into the ocean, which means isopycnal surfaces and thermocline are being pushed down, which raises the sea level. So you get high sea level in the middle of the subtropical gyres in both the Atlantic and Pacific and Southern Indian Ocean. Indian Ocean is always complicated because of this exchange with the Pacific and the monsoon circulation and so on and so forth. There are similar bulges in both hemispheres, obviously. So here, upwelling is bringing up the thermocline and creating cold waters and lower sea surface. So if you go from the Galapagos to the New Guinea coast, for example, the sea level will rise by about 50 centimeters. If you go from the equator to the middle of the subtropical gyre, it'll increase by about 2 meters. So there are slopes in sea level, which obviously give us geostrophic currents by the previous relations we have looked at. Okay? So altimeter is a clean way to estimate surface geostrophic currents. The variance here is deviations in time from the mean sea level heights, which give you a sense of the wiggling that we have talked about in the Kuroshio and Gulf Stream extensions, other western boundary currents here, Brazil Malvinas, East Australian current, the Agulhas outflow and the Agulhas retroflexion, and so on and so forth. Okay, there are places where sea level variance is high. It is related to these eddies, and so on. We had seen. Okay. Geostrophic flow at depth then turns out to be critically dependent on density, because the approximation we made near the surface about ignoring variability of sigma cannot be done anymore. So we had derived this equation: Pz at the deeper level was surface pressure plus this integral z to eta g rho dz, which we estimated as ps plus g times this water column weighted density times eta minus z. Okay, so we will see that this ends up being two terms when we take gradient of pressure. So if we took z hat cross grad p of this, then we are going to end up with g of this average density times z hat cross grad eta, that's the sea level, plus g times eta minus z hat cross gradient of the density itself. Even though we took the weighted density in the vertical, it has horizontal variations, so the pressure gradient at depth is a combination of two terms. One is related to sea level variations, which is independent of the depth. This has no z in it, right? This is dependent on horizontal gradients of density, which is dependent on the depth from the free surface. Magic happened, right? So if these are in opposite direction, then they will compensate for each other. Why are we saying that? Because we know already that the deep ocean has very little motion, so we need them to be compensating each other. So writing the geostrophic current vector, it's 1 over f rho ref z hat cross grad p, where we replace grad p with this, so 1 over g over f rho ref times average density z hat cross grad eta, the sea level gradient term, plus eta minus z times z hat cross grad of the average density, so the horizontal gradients of density, where we have now approximate the column density as rho ref, which is fairly valid. So this is not ignoring density gradient, it's just making an approximation in the vertical, because remember this angular bracket rho is a vertical average, not horizontal. So you end up with two terms, approximately g or f z hat cross grad eta plus g times eta minus z or f rho f z hat cross grad average density. Okay, we don't replace this with rho ref, we only replace it in the denominator. Okay, so instead of, you know what happened here. Okay, look at this term and make sure you understand, but the figure will make it very obvious. What is the second term? It's basically the compensating term, but it's also the thermal wind term, right? Horizontal gradients of density give us vertical variations in geostrophic currents. So this u is at depth. So we are not explicitly writing it at du dz, but we have approximated geostrophic currents at the surface with the grad eta term, and we are now approximating at depth, so we are looking at the vertical shear in that sense. So this is thermal wind. So u varies with depth if there is a horizontal density gradient. Okay, so we are still in the large scale thermal wind balance. U goes to 0 in at depth in equation 912. Then at depth z equals minus h if the water column depth is much larger than the sea level, which is almost always true because sea levels vary at most by a couple of meters depending on the distance, whereas the depth is always several kilometers of the ocean. So you can write the previous equation as h over rho ref, gradient of the density, as approximately equal to gradient of the sea level, and you can divide by n squared, where n squared is minus g over rho ref d sigma dz, which we can approximate for demonstration purposes only, ignoring salinity effects, as g alpha t, where alpha t is the thermal expansion coefficient times dt dz. Okay, this we are doing just to show the next figure to explain how sea level gradients are compensated by temperature gradients, or in reality density gradients, to create near zero pressure gradients at depth so that geostrophic currents go to zero. So many words, but look at the figure. Okay, So isopycnal slope is approximately equal to g over n squared h times the magnitude of the free surface slope. So here is the free surface. It has a dip here and it has a rise here. If you look at isotherms, when you add salinity and do it properly, these are actually isopycnals or density surfaces. To create near zero gradient in pressure at depth to produce near zero current speeds, free surface gradients are compensated by isopycnal slopes. That's all this is saying. Long story short, if the free surface dips, isotherms dome. If free surface domes, then the isopycnals dip. How much is the free surface and the isopycnal slope fraction? What is the ratio like? You can do that by looking at g or n squared h, which is about 400, which means if free surface moves by about 1 meter, isopycnal surfaces have to move by 400 meters. That's all. Okay? So we are producing near zero geostrophic currents at depth because surface elevation or sea surface height or sea level variations are compensated by isopycnal variations in the opposite direction. Okay? This is a pressure gradient, that is a pressure gradient. If they're in the opposite direction in our equation, then we compensate them out and create near zero velocities. So the observations are then still consistent with geostrophic balance as long as pressure gradients by sea level variations are compensated by isopycnal slope variations. That's all.